Alright, this video is going to be that on crystal structure. So let's talk about crystal structure and a crystalline solid. A crystalline solid possesses a rigid and long-range order. What we mean by long-range order is it repeats itself for a very large amount of times. In a crystalline solid, atoms, molecules, and ions occupy specific positions. And those positions are very predictable because we know exactly where they are. It's very ordered. An amorphous solid is the opposite. It does not possess well-defined arrangements or long-range molecular order. You don't have these repeating predictable units like you have in a crystalline solid. Speaking of units in a crystalline solid, a unit cell is the basic repeating structural unit of a crystalline solid. A unit cell will look like this, and as it obtains long-range and rigid order, these unit cells build upon themselves as the crystalline solid grows. These unit cells can be defined by their lattice points, those black spheres that you see at the corners. At those lattice points, there will be an atom, a molecule, and an ion. Now, they'll be in different arrangements depending on the type of packing that would be within the unit cell. There are 7 basic unit cells. We're going to focus on a simple cubic cell to give us an idea about how spheres and atoms, molecules, and ions pack into different arrangements. So we're first going to talk about 3 different types of cubic cells. What I want you to notice in each of these graphics as we go from the left to the right is start to get an idea about how many atoms are able to fit within a unit cell. Okay, and how they're able to fit on the unit cell. You can notice in this one all of them are just kind of grabbing a corner, whereas this one has one in the center where they're all grabbing a corner, where in this one you have them grabbing a lot of different faces. This is a progression of how you can fit more atoms in a particular unit cell and become a closer packing crystalline solid. So let's first talk about a simple cubic cell. The arrangement depicted in figure A was if you took a sphere and you put it in its long-ranged order, it would be in contact with 6 other spheres. In a simple cubic cell, the coordination number would be 6, okay, because it has 6 immediate neighbors. Figure B gives a more accurate, view of what parts of these spheres would actually make it into the unit cell. So as you can see, there's a lot of room in these spheres that's not even inside of the cell. In fact, in figure C, you can see that only a corner, or 1/8 of each of these spheres, actually fits into the cell. So albeit you have, in the 2 layers of this unit cell, 8 spheres, you really only have 1 whole atom packed into each of these unit cells. And we'll be working with that later. Okay. You can look at an arrangement of identical spheres in body-centered cubic cells. So you can see the coordination number actually increases. Okay. A body-centered cubic arrangement differs from the simple cube in that there's a second layer of spheres that fit into the depressions. See there's 1 layer of sphere, and it fits into the depressions of the next one. So you see 1 layer, another layer, and another layer of 4. It fits into the depressions. All right. Each sphere can now be in contact with 8 neighbors, and it has a coordination number of 8. Now if we look at the figure in diagram C, you can see that there's 1 whole sphere within each of these unit cells, and 8 spheres that are only 1/8 of a sphere. So in a body-centered cubic cell, there are a total of 2 atoms. A total of 2 atoms per unit cell. Now this next slide is going to break down what I meant by 1/8 of a sphere, or 1/2 of a sphere. If you are on a corner of a unit cell, you can see how this sphere within a larger unit is broken up into 8s. There's 4 on this side and 4 on that side. if you are in that arrangement, or on the corner of a unit cell, only 1/8 of your sphere will actually make it to packing that unit cell. If you're on an edge of a unit cell, you can see this one, it's on the edge and it's the middle of these two cells, 1/4 of your sphere will make it into a unit cell. And if you're on a face of a unit cell, 1/2 of your sphere will make it into a unit cell. So let's talk about the number of atoms per unit cell. I was talking about that before. Simple cubic has 8 atoms, each on a corner. So 8 atoms with 1/8 of the unit cell will be 1 atom per unit cell. In a body-centered cubic arrangement, you'll have 2 atoms per unit cell. That will be 1 atom in the center. That's that +1. And you have 8 taking up corners for a total of 2 atoms per unit cell. And as you get to face-centered cubic cells, this is the closest packing. You can have up to 4 atoms per unit cell. You have 8 atoms. You can see 1, 2, 3, 4 at the corners, contributing 1 atom. And you have 6, you can see at each face, contributing a half sphere each, giving you a total of 4 atoms per unit cell. So you can see as you add, going from left to right, all right, you add spheres in various arrangements, you can increase the amount of atoms that you can get per unit cell, depending on whether you're a simple cubic, body-centered cubic, or face-centered cubic packet. So in each of these structures, there's a relationship between edge length and atomic radius. Okay, so in simple cubic, the radius of one sphere, so this is 1/8 of a sphere, but this represents, the radius of it. The edge length is 2 of that radius. As you move on to body-centered cubic and face-centered cubic, the edge length A is represented by a different mathematical function. All right? In body-centered cubic, the edge length is 4 times the radius of a sphere divided by the square root of 3. And in face-centered cubic, the edge length is depicted by the square root of 8 times the radius of the atom. So there's 2 types of closest packing. Closest packing in which you can have a coordination number of 12 and 4 atoms per unit cell. There is hexagonal close packing and cubic close packing. It depends on which depressions you pack your spheres in. Cubic close packing is the same as the face-centered cubic arrangement we learned earlier. So the hexagonal close packing. And the cubic close packing. Both of these would have unit cell structures similar to that of face-centered cubic. So let's do a problem with this. Let's talk about gold crystallized in a cubic closed pack structure. Okay? So, the face-centered cubic unit cell. And we say it has a density of 18 or 19.3 grams per cubic centimeter. And then I say, calculate the atomic radius of gold in picometers. Where would we start? Okay. We want to calculate the radius of the gold atom. For the face-centered cubic cell, the relationship between radius and edge length. So, face-centered cubic is just like the cubic structure right over here. And we can see that the relationship between the edge length A and radius is the square root of 8r. So we're going to use that. So therefore, to determine the radius of the gold atom, we need to find A. So the volume of the cube is that edge length cubed. And so A is equal to the cubic root of the volume. So if we can calculate the volume of the unit cell, we can calculate the edge length. And we are given the density in this problem, density being mass over volume. So if we solve for this volume, we'll be able to solve for the edge length. This is the sequence of steps to go about when doing a problem like this. You work from the density of the unit cell to the volume of the unit cell using the density formula. Once you have that volume, you find the edge length, that A of the unit cell, and then the radius of the atom. So we know the density, okay? In order to determine the volume, we need to find the mass of the unit cell. This is where the closest packing spheres come into play. Because it's a face-centered cubic cell, there are 8 atoms, each at corners, and there are 6 atoms at each of the faces, corresponding to a total of 4 atoms per unit cell. Now, if there's 4 atoms per unit cell, 1 mole has 6.02 Avogadro's number of atoms, and that number of atoms of Avogadro's number has a weight of 197 grams. The amount of grams that you'll have per unit cell is 1.31 times 10 to the negative 21. Now we have both mass and density, and we can solve for volume, giving us 6.79 times 10 to the negative 23rd. We plug volume back in to the edge length formula. And now we have our edge length, and we're going to use it to find the radius of the sphere. That radius of the sphere comes out to be 144 picometers. That does it for our crystal structure video.